All right. It's now 12:30, and we're now recording the lessons. So those of you who haven't muted up yet, make sure you go ahead and do that. I think I got everybody. All right. So today's lesson this is what I call a "Yeah, I got it" lesson, where there's two groups of students that come across this lesson. One of them is that they have troubles with S spaces, and it's a great review for that. Another group is the "Yeah, I got it" group. And what I mean by that is students will be like, yeah, I got it, until it gets to the exam. Okay, so you got to practice this stuff, even though it seems easy up here when I'm guiding you through it. It's something else entirely to use a PK table or go through these various questions on the exam. So with that in mind, again, today's going to be a lesson on acid-base chemistry, and a lot of that is we're going to be starting to move into the arrow pushing. I think we got cyclohexanes coming up in the chair confirmation, which is more review of 3D thinking. And then we're moving into nucleophilic substitutions versus eliminations, basically when something's acting like a nucleophile versus when something is acting like a base. And I put up some definitions up there. Something is basic, or is a base, usually when it has a pK that's greater than 16, and they tend to be bulky, and they tend to be nucleophilic when the pK is smaller than 16. Now, why am I spending the time going through this? That's something a little bit more lecture-based. I think it's important to note the difference between the two. There's a little bit of nuance here. Usually with a pK of 16, you're talking about alcohols. So alcohols can act like an acid or a base. Based on these definitions, which one of these is more likely to act like a base and which one of these is more likely to act like a nucleophile? So which one's more likely to act like a base, A or B? A. Why the one on the left there? Right, it's very bulky, okay? So remember what's going on here is, the reason I say bulky is we got to remember these carbon groups, these methyl groups and ethyl groups are very large. So it has enough room to deprotonate, let's say the 2-chloropropane here, and to go through an elimination. And I'll show it as, oops. There, I made a mistake. There we go. Let's remove a proton there. And undergo an elimination. With our product being propene. Now, in the case of this negatively charged methoxide here, there's plenty of room for it to undergo a nucleophilic attack. It's small enough to sneak in there and attack the carbon itself. So instead, what you see here is instead of just removing a proton, it goes in, backside attack the carbon here, and thus removing the chlorine, exchanging it in its place. This is just a setup for when we start talking about reactions, because usually you have to figure out whether a reaction is going to go through a base reaction or if it's going to go through a nucleophilic reaction. And the product here will be something like this. Any questions on that? Okay, let's get into some meat and potatoes here. First, we're going to start using the pKa table and how to really use it. Now, the fun part for me is that the proton on the pKa table, that's going to be the acidic one, is listed in red. Now, for me, that looks like black to me. So the whole thing can be a little hard for me to read at times, being colorblind. So the top part of this chart is more acidic. The bottom part of the chart is more basic. Remember, high acidity is low pKa. from here on out, and I want to put this in your notes, P stands for negative log. P stands for negative log. So pH is negative log of the H concentration. Negative log of Ka is the pKa. And because of the negative sign and the logarithmic scaling, it reverses. A high Ka gives you a very low pKa. A high H concentration gives you a low pH. So, right now I have an example up here of a multivariate species. This is ammonium. And it can deprotonate a few times. This tends to trip up students. Remember, when you're looking up a pKa, you're really looking at the equilibrium. Okay? So you have to make sure you're looking at the right balance beam, if you will. So on this first one here, let's go look up the pKa of the ammonium. So it's 3 protons and then 1 methyl group. And that's given right there. Does everyone see that? I know it's a little small on the screen. Okay. Now, when you come to an exam, you're going to be looking at this whole chart. And it will take you time that you don't have on the exam. So you have to familiarize yourself with roughly where these functional groups are at. And that takes practice, okay? So I'd recommend memorizing a few of them, like ammonium here, okay, NH3. So that pKa is 10. Now let's go ahead and see what the pKa of this one is. Do you expect it to be a higher pKa or a lower pKa? Going back to the example here. It's going to be higher. Why? There's a lot of reasons. Just give me one. There's less hydrogens. It's going to be less acidic, right? Because it's no longer positively charged. So let's go ahead and look down the list here. It's right here. Okay. And I believe roughly it's right here. Sometimes you have to find things that are analogous to it. Remember, it's not an ethyl group that's coming off. That's the ET there. We have a methyl group coming off, but it's going to, chemistry-wise, it's going to be very similar. So let's write down pK of 38 here. Okay, we have a pK of roughly 40 and a pK of 10. That means the pK of 10 is 4 times, this species here, is this what it's saying? This is 4 times more acidic than this? Is that what that means?
Yeah, so it should be.
Is this a thought experiment?
1.00.
No, why? That's a great answer. I've got a lot of students this morning with that.
Yeah, I think that should be like 39 or something.
It doesn't. And the reason that is it's easy to think of the pKa as a linear relationship. Remember, it's not linear. This is 10 to the power of negative 10.
38.8. Yeah.
Another way to put it, if one molecule deprotonates, there's 10 to the 10 that don't. Here, the relationship is if for every one molecule that deprotonates, there's 10 to the power of 38 that don't. And if you take 10 to the power of 38 and divide it by 10 to the 10th power, you're going to find out it's a massive, massive difference in acidity. Okay? So that's how you go from the logarithmic scale to the linear scale.
Yeah. So yeah.
Now, this question I got everybody on during the morning, actually. And I will review, I think, the problem here. All right, let's say we got a solution of water or whatever. And its pH is, let's say, 8. What's going to be the dominant species here? A, B, or C?
I don't know if it's correct, but these guys definitely smarter than I am. 75, yeah, that's different.
Hang on, it is kind of hard for someone to hear me. I can't hear them. Oh, they're okay. Give me 1 minute, guys. I'm gonna have to stop sharing for just a second and see the list here. And there we go. Okay, can you hear me better now? Online. I've muted everyone but me. All right. All right, so we have a pH of 8. The environment is 8. Which one's going to be the dominant species here? A, B, or C? Go ahead and type it in the chat box. Don't worry. This morning they were all over the place. We had it actually split 1/3, 1/3, and 1/3. So go ahead and throw your guess out there in person. So we got a C, A, B, A. All right, got a lot of A's and a lot of don't knows, a lot of C's and B's here. So remember that when we're dealing with pH, a low pH means what? A high concentration of H+. And it's going to look for somewhere to land. What I don't have on here are the H+'s. I don't have a balanced equation. If you really want to balance this, you'd also put in the solvent. I'm being a little, let's say, shorthand with it, okay? And so Le Chatelier's principle comes into play when we dump in a whole bunch of H+. Can anyone explain to me what that Le Chatelier's principle means? It's coming up in your organic chemistry lab too. I'm looking at the chat box too. There's a few ways to define it. It means if we change an equilibrium in thermodynamics, so we're talking about thermodynamics, the reaction will respond to a stressor. I really like that. For now, if we dump a lot of H+ into the solution, it's going to shift it to the left. Okay, think of the H+ as needing somewhere to land. Okay, it needs somewhere to go. So it's going to land and be a part of the NH3+. Give me a different pH. Give me something fun here. You guys come up with the problem. Pick a number, it doesn't matter. 14. Let's do pH 14. What's going to be the dominant species? I'm going to go right down the row again. All right. A. A was the answer. I'm writing it up. C. B. B. A. B. A. And again, we're kind of a little bit all over the place, which is totally fine. I expected that with this problem. Now, with the pH being between the two pKa's here, it's the middle one. Okay? Now, I think confusion comes where people are trying to compare the pH. She says that the reaction arrow always goes in the direction of the one with the highest pKa, and we'll go to that example in just a second, okay? So this is just a little bit of a different problem than what you're used to seeing. Let's pick another one. Let's do pH 40, which really doesn't exist, right? So it's extremely basic. If you dipped your finger in that, it would probably melt off. And pH 42 can't exist. In that case there, what species would dominate? C. Okay. Now, that's a way to compare pH to pKa. And you have to keep in mind what's happening with the chemistry. I'm not going to promise you this problem will show up, but I'm writing the quiz next week, and you can probably expect it. Okay, hint, hint. John wrote the quiz this week. Let's continue on with our lesson here. I'm going to minimize some stuff here. We're going to do everything except for calculate the equilibrium constant. That's kind of a memorized way of doing things. And unless Dr. Vickery goes through it, I will not be. It'll just be extraneous stuff to do. So let's start with that first one here. Now, these are very similar to the problems that Dr. Vickery was doing in class. This is coming from my problem set 2. No, wait, 3, I think, sorry. But problem set 2 and 3 have a lot of these acid-base questions and different ways of wording it. So we'll use the pK table to solve this, and then we're going to go use it to kind of dip into ARIO. And then from there, we'll see how far we can get. All right, so at this point, you need to find one of these species as the base and one as the acid. Once you're on the right side of the equilibrium arrow, that's the conjugate base and the conjugate acid. It doesn't matter in which way the equilibrium arrow will go. It's just the way we define things. Conjugate's going to be on the right-hand side. So let's define which one's going to be the base and which one's going to be the acid here. Now, because I labeled the protons, this should be pretty quick. What's A? Yep, it's going to be the acid because it's got that nice negative charge. Or, yeah, base, sorry. Come on. This one's going to be what? Acid. Now, in terms of the equilibrium arrows, or sorry, the reaction arrows here, we're starting to use them here. It's going to grab that proton. And then we're going to draw the species of the conjugates on the other side. One thing to note, if you're having issues with this, the charges on one side should equal the other if you drew the reaction correctly. Now, this isn't Gen Chem where we get super specific about things, like making sure you got the solvent in there and stuff like that. We tend to focus on what's I would call important. That's a little bit of a, you can't tell I don't like teaching Gen Chem. Okay, so we're at this point here. Now, we have to talk about the conjugate base and conjugate acid. If it's a base on the one side, it's what on the other? Conjugate acid, okay, because it's going to be considered the acid going the other direction. And this is going to be the what? Conjugate base. Now, it's our job to figure out the pKa's for the acids. There's a few ways to look at this reaction. Now, I'm going to do it all on the same reaction arrow. If you have issues with this, what I would recommend is these are 2 different reactions that are occurring and they're transferring a proton across. So you can draw both left to right, going from acid to base if you get really stuck with this. It's when they combine the 2 that students have issues, okay? If you guys need that, I'll be more than happy to go through it, but I don't know if we will. So let's go to the pK table. Let's, we've already looked up the acidity of this. Anyone remember what that was? What's that? Yeah, 38, pK of 38, yep. Might be a little bit different. Let's take a look. Here, because we have 2 ethyl groups, it's pK 40. It's slightly different. Now, we're looking at the pK of acetylene, the triple bond there. You see here, it's pK of 25. Let's write those in. All right. Which way does the equilibrium arrow go overall? Dr. Fricker went through a few different ways of solving it. Y to the right. And we're mixed up on the chat box again, too. It's got the weaker acid. How do you know it's the weaker acid? Right. So there's two ways you can define it. One is it goes away from the one with the lowest pKa, because that's going to be the strongest acid. Another way you can do it is you look for the highest pKa, and it's going to go towards that. But make sure you're labeling the acids in both of that. Okay. There's a few systems you can use, and the rule will always be true because it's pKa. pKa never lies. Okay. And a quick story. One of the most cited papers in analytical chemistry was done by an undergrad who made the pKa tables back in, like, I think the 80s. I think it's got 4,000 citations. So if you ever think like the work that you're doing in the lab doesn't really matter that much, the undergrad didn't even think that anyone would read his paper, and it's, again, the most cited paper since basically science came out. So anyway, that makes it a little interesting. So why is the triple bonded carbon more acidic than the nitrogen here? I thought carbons were like notoriously basic, especially negatively charged ones. It is because of the triple bond. So let's go ahead and talk about ARIO and review that one more time. So I'm going to pull up the pKa table at the same time here. So I'm going to kind of minimize this. Now this is in relative order, but this is a case where the atom is being beaten out by the orbital effect. And normally, orbitals matter the least. So let's take a look at some of these effects here. So normally, the electronegativity matters, but you also have to consider atomic size when you're dealing with the first one. Notice here that HI is more acidic than HF. I thought fluorine would be more electronegative than iodine. Why is HI more acidic then? Much larger, yes. Okay. The fluorine and the hydrogen are relatively the same size, so the sigma bond they make is incredibly strong due to them having about the same size. With iodine being so much larger than the H, it's much easier for it to let go and be more stable. A good way to think of it, and maybe this is a bad analogy, I like to think of HF as like the moon and Earth, and the difference between H and I being like Earth and like a small asteroid like going out of our orbit. Maybe that doesn't work for you guys, but that's how I think of it. This is why H2S is more acidic than water, H2O, even though the O is more electronegative. Okay, so keep in mind those sizes, and a good way to do it is just practice. There's little exceptions here and there. The big one you see is the thiols versus the alcohols, again, HS versus HO, and then iodine versus fluorine. If you don't remember the electronegativity and atomic size stuff from the periodic table, go open the book up and review it. You should know that from general chemistry, or I'm assuming you know that from general chemistry. All right, next effect is resonance, and I'll come back to that after our next example that I'll do up here. Induction is kind of like electronegativity, except it's not the atom that the proton is directly attached to. Let's look at an example here. So here's some alcohols here. If one of the R groups is CF3, you're getting that strong inductive effect from the fluorines, even though the fluorine is not the atom the hydrogen is directly attached to. So you're seeing a pull across the whole molecule, and it's pulling away the electron density away from that proton and making it more acidic. Think of pulling away electron density or finding ways to stabilize it through resonance. Finally, we get to the sp, the orbitals. Sp is more acidic. Let me draw this out. SP is more acidic than SP2, which is more acidic than SP3. The more S character, the more acidic. And I like to think of it as the more S character you have, the more the electron density between the carbon and the hydrogen, an example, the more it pulls it away from the proton because it's going to be closer to the nucleus because it's more S, right? S is the orbital that is directly around the atom, okay? With P's, it's further out there. So I like to think of it as CH. And this is just a metaphor here. So when I say more S character, SP here has one S orbital and one P orbital. The two are mixing together. You have one S over the total two. Does that make sense? So that's 50% S. SP2 here has how much S character? 33%. Everyone see how he calculated that? He's got a total of 3 orbitals that are being mixed up together. 2 of them are P, 1 of them is S. So he's doing 1 divided by 3 there to get 33%. And lastly, SP3 has 25%. So I like to think of it as pulling the electron density away from the proton. All right, we're going to skip ahead here to another example here. I'm going to create some room. We'll probably go through, I think, 2 more examples, and then we'll go right into the quiz. Are there any questions so far before I do more examples? Is there something that anyone is stuck on? Okay, so again, the 2 lessons here. 1, learn how to use the pKa table. 2, you should start understanding the relative strength of acids based on the ARIO chart. Okay, you're not expected to memorize pKas as I understand it, but it's a good idea to start nailing them down, especially those of you going into biochemistry. It doesn't go away. pKa never goes away. It's a good idea to get a few of them in your head. So let's go ahead and do this one here. All right. Walk me through it. What's going to be the species that we need to counteract this one? Yeah, just a negative charge there, right? Yeah. Thank you. Okay, so let's start labeling this out. Is this base or acid? Base. Which one's this one? And then conjugate what? Oh, not conjugate acid, conjugate base. Right, because it was acid on the other side, right? Remember, it flip-flops on you. And finally here, conjugate acid. All right, let's look up pKs here. Now I'm helping you out a little bit. The analogous one is going to be this one here, 16.5, because the cyclohexanol has 2 carbons coming off and also has an H, okay? And that's close as we can find to the table there. So let's write in. And then over here, we said the pK was roughly 40. Which way does the equilibrium go? Yep, to the left. The dominant species are going to be on the left. So this is an example of A and the ARIO. Both oxygen and nitrogen are relatively the same size. The oxygen being a little bit smaller due to the increased electrons. So you're getting a greater pull towards the nucleus, but it's not so much to really make that much of an effect. The big thing in play here is going to be what with A? Between the nitrogen and the oxygen. So I set atomic sizes out. So what's that leave for us on A? Electronegativity, yeah. Okay, I'm gonna go do, I think, one more example here, and then we'll go straight to the quiz. I wanna give you guys a few extra minutes. Normally it's supposed to be 10 minutes, but those of you with SSD, of course, always start the quiz a little bit earlier. We're running short on time, so I'm going to leave the labels in place. So again, this is coming from problem set 3 here. And we should be able to recognize at this point that the acid that I need right here is going to be this species. And the conjugate acid on the right side here is going to be that species, but protonated. All right, normally this is when I load in the pKa table. I'm not going to this time. Which one's going to be more acidic based on ARIO? Or which way does the equilibrium arrow go? Incorrect. Sorry, I have to like turn around to do it for you. So what's the answer then? It's going to be towards the right. Why is the right going towards the right answer? Which one? ARIO. I mean, take a guess. Resonance effects. Okay. So this has a pK of 10. That has a pK of about 16.5. It's roughly 600 times more. No. Sorry. It's about 1,000,000 times more acidic. Okay, and it has to do with that negative charge being stabilized through resonance. So sometimes when you're dealing with learning the stability of these things, sometimes it's easier to look at the base and ask yourself, why is this negative charge so stable? Or comparing the negative charges of the stability. So this reaction has the equilibriums go to the right with the pKa of phenol, which is that benzene ring with an OH on it. That has a pKa of about 10. And we can find that on the pK chart. Oh, where is it? It's right here. So it represented by that species right there, giving us 9.9. Okay, yeah, so this is a lesson of, yeah, I get it, but again, it can be a little confusing the first time you go through it. I highly recommend you do problems on this. There's a lot of things I wish I had more time to go through, but you have to pick it up while you practice. Most notably, learning to use that PK table quickly and efficiently. That's something I can't teach up here to you. That just takes practice of you going through practice problems. Okay, so I'm trying to show you how I'm using it, but it's on you to kind of get really good with it actually pretty quickly. So with that in mind, again, I have more practice problems for you guys. Let's go ahead and open up the quiz. You have, I think, until 1:30. Joe wrote this one, so it's a little trickier than usual, but you guys will be fine. You guys proud from uploading, or you have any questions for me? Of course, always email me. Acidity is one of those topics that it's more tricky than what it looks at first glance. Okay, I'm going to stop sharing for just a second so I can load up the quiz. And then I'm going to